All right, so one of the things that we talked about yesterday that was new was the Pythagorean Identities, and my advice would be write them as many times as you need to so you have them memorized. So the first one is that sine squared x plus cosine squared x equals 1. And then if I divided each of those by cosine, I'd end up getting tangent squared x plus 1 equals secant squared x. If I divide each of the original ones by sine, I get 1 plus cotangent squared x equals cosecant squared x. My advice is write them down on your test as soon as you get them, okay? Hopefully the other stuff you can remember, but these three are definitely ones that not only you have to memorize, but you have to be able to manipulate. So you have to be able to move them around. So that's why it takes a little bit more comfortability with them. All right, so number 1 said simplify the given expression, and it was secant x minus 1 and secant x plus 1. So what did you do with those?
I went back and put them into perfect squares, so it'd be secant squared x minus 1.
Good. So if you didn't know that, if you didn't recognize that it was a perfect, it's going to end up being the difference of two squares. You can multiply it out by foiling, and I'd end up here. These are going to cancel, and I get secant squared x minus 1. So you want to look back on your trig identities, and the one in the middle there has a secant squared and a 1. So if I just did secant squared x minus 1, what's left on the other side? Tangent squared x. All right, number 2, same set of instructions. Simplify the given expression, secant squared x times 1 minus sine squared x. So a couple different ways to do it. What's one way?
I turn the 1 minus sine squared x into cosine.
Good. So another Pythagorean identity, right? So 1 minus sine squared x is cosine squared x. And then what?
And then I did secant squared x over 1 times 1 over secant. Or no, you know what? I didn't do that right.
So secant squared x becomes 1 over cosine squared x, right? And then the cosine squared x's cancel. And I just left with 1. Anybody distribute it in? Because you could do that too. Okay, that works too. All right, then the last one says, simplify the given expression, secant x over cosine minus tangent x over cotangent. What's one way to do this one?
I flipped the cosine, so it was secant times secant.
Okay, so you brought the cosine to the top, which makes it secant, which becomes secant squared x. And then did you do the same thing with cotangent?
Yeah.
Yep, so cotangent comes to the top. That would be tangent times tangent, or tangent squared x. Go back up to that first one that we use, which says tangent squared plus 1 equals secant, and solve it by subtracting the tangent squared. And I get 1. Anybody find the least common denominator? Because you could also do that here. This is one of those that it would take a lot longer to do that way, but you definitely can do it that way. So if I do that, just so we can walk through that process, to find the least common denominator, I have to multiply these by cotangent and these by cosine. And I end up with cotangent x times secant x minus tangent x times cosine x all over cosine x times cotangent x. And then cotangent would be cosine x over sine x. Secant is 1 over cosine x. Minus tangent is sine x over cosine x times cosine x. All over cosine x times cosine x over sine x. So then these cancel, and I get 1 over sine x. These cancel, minus sine x over cosine squared x over sine. And then I got to work with the numerator, so I need to make this one term. So sine over 1 has to get multiplied by sine in both the top and the bottom. And I get 1 over sine x minus sine squared x over sine x all over cosine squared x over sine x. So then my numerator becomes 1 minus sine squared x over sine x all over cosine squared x over sine x. My numerator 1 minus sine squared x is cosine squared x over sine x, all over cosine squared x over sine x. Numerator and denominator are both the same, which means this is 1. So this is one of those examples. Yesterday we talked about that it helps a little bit to move those denominators sometimes. This is a major difference, right? The left side took 2 steps. The right side took a lot more. Doesn't mean that it's wrong. It's not like there's no reward for, well, time, I guess. You're not wasting your life doing trig identities. That's your time is your reward. But they would both earn equal credit on your test. Obviously, the right side is going to take time away from the rest of your test. All right, questions on the warm-up. Number 7 on the homework. Some of them were a little bit different, like the number in the front was different, but it said use the fundamental identities to simplify the expression. Use the table feature of a graphing utility to check your result algebraically. So first thing you want to see is that this is one of your co-functions. So what's the equivalent of cotangent pi over 2 minus x? Tangent. So this becomes 4 tangent of x times cosine of x. And then tangent is sine of x over cosine of x times cosine of x. And then the x's cancel, and you end up with 4 sine of x. So basically the table feature just allows you to, if you had typed them both in, like if you go to your y equals and you type in this equation and you type in this equation, you should see that your tables match. That's all. But you're not going to have your calculator, so don't rely upon it to check your answers. Okay, just make sure that you are good without it. All right, 4 terms tells you factor by grouping. So I'm going to group these together. You could take it out of 2 from the beginning also, but you don't need to. You can wait. So this would be 2 secant squared x, and this would be secant x minus 1, and then take out a negative 2, and I get secant x minus 1. So then I get secant x minus 1, 2 secant squared x minus 2. And then the last thing you can do is take out that 2. So I could put it here. I could put it all the way at the front. 2 secant x minus 1. And then secant squared x minus 1. This is one of your trig identities, right? So tangent plus 1 equals secant, which means secant squared, which means if I move the 1 to the other side, this would be 2 secant x minus 1 times tangent squared x. And then that's as far as you can go. So same rules apply for factoring. If there's 4 terms, you're going to factor by grouping. 3 terms, you want to factor it by doing the first and the last, that kind of thing. Number 11 says perform the addition and use the fundamental identities to simplify. So again, your red numbers might have been different, but it was the same concept. This time, they're different denominators, right? And it's not an easy just flip up. Like I can't take sine and move it because it's got with the 1 with it. I could do that with cosine, but it doesn't really help much. So this time I'm going to find a least common denominator, which is going to be cosine x times 1 plus sine x. And then this is going to get multiplied by cosine, and this is going to get multiplied by 1 plus sine of x. So cosine times 7 cosine x is 7 cosine squared x. And then 7 plus 7 sine x times 1 plus sine of x. I'm going to FOIL that out. I get 7 plus 7 sine of x plus 7 sine of x plus 7 sine squared x. Or 7 plus 14 sine x plus 7 sine squared x. And that's going to go with my 7 cosine squared x. Squared x. And all of that goes over the denominator, which was cosine x times 1 plus sine x. So then from here, you can combine your like terms, okay? There's a cosine and a sine, which can't combine yet, but there's a 7 and then the 14 sine x. So the fact that there's a mix of sine and cosine is telling you something's got to get eliminated here. Every single one of those numbers is divisible by what? 7. So if I start there, I get 7 cosine squared x plus 1 plus 2 sine x plus sine squared x all over cosine x and then 1 plus sine x. So what do you see in that numerator that can be replaced? Good. What's cosine squared x plus sine squared x? 1. So now I've got 7, 1 plus 1, which is 2 plus 2 sine x over cosine 1 plus sine x. Now I could take out another 2, so I'd get 14 on the front. 1 plus sine x over cosine x. 1 plus sine x. The 1 plus signs cancel out, and I get 14 over cosine, but you don't ever want to leave a function in the denominator. When I bring cosine to the top, it becomes what? Secant.
Instead of taking the 7 out, could you have added 7 cosine squared x plus 7 sine squared x to equal 7?
So you just got to make sure that you realize that it's a 1 that you're pulling out there. That's fine. You would technically be grouping them together, pulling out a 7 and then making it 1. But if you can do that all in one step, that's fine, just as long as you realize that's what that is. Just don't make the mistake of doing like a 7 plus a 7, because that is where I could see people going wrong with that. Okay, and then 12, use a graphing utility to determine which of the 6 trig functions is equal to the expression. And again, I wouldn't rely upon my graphing utility, okay? But what it's telling you to do is, if I solve it, can I type that into the calculator and would I get the same graphs or the same table? So I'll start with sine of x times cotangent of x plus tangent. You can distribute in the sign, so it'd be sine of x times cotangent of x plus sine of x times tangent of x. Sine's going to stay as sine, but cotangent becomes cosine x over sine x. And then sine stays as sine. Tangent becomes sine x over cosine. So on the left, it's going to cancel, and I end up with cosine of x plus sine squared x over cosine x. Now the denominator on that cosine is 1. I need them to be the same, so I'm going to multiply both the top and the bottom by the cosine over here. And I get cosine squared x over cosine plus sine squared x over cosine. Cosine plus sine is 1 over cosine. And then bring the cosine to the top, and it's secant. So if you were to type that and this into the calculator, this is probably just messing the parentheses. You'd see that they would give you the same graph, and that's how you can compare them. Questions? Everybody's good on homework? Okay. 5.2. It's called verifying trigonometric identities. So the good news is everything you needed to know for yesterday is the same thing you need to know for today. There's actually absolutely nothing new. The difference is that instead of just simplifying it, they're going to tell you this equals this, and your goal is to get them to be equal. In my opinion, it's actually easier because you know where you have to go. You know when you're done, right? With yesterday's section, you were like, is that as far as I can go? Is that as simplified as it gets? Now you'll know. When the left side equals the right side, you know you're done. You're good. So same reference sheet. Again, if you haven't memorized the stuff on this sheet yet, you need to make sure you have all of this stuff memorized. The reciprocals, the Pythagorean identities, the even, odd, and the cofunctions. And then this is some guidelines to actually working through. This is in my opinion, the hardest thing to teach, because I can't tell you step 1 is this, step 2 is this, step 3 is this, because each one is different. So the very first thing says work with each side of the equation independently of the other side. Working with the more complicated side first. So when you look at your two sides, if the right side just says sine and the left side has an addition or subtraction or reciprocal functions, you're going to leave the sine alone. You're going to work with the other side. Analyze the identity and look for opportunities to apply the fundamental identities. So you're looking for things like cofunctions and even and odd functions, Pythagorean identities, and reciprocal functions to replace what you've got already there. And then it says try using one or more of the following techniques. So rewrite the more complicated terms in terms of sine and cosine. So if you had just basic sine and cosine on one side, you're not going to mess with that side. You're going to do the other one. Factor out greatest common factors if you've got them. If you're starting with a fraction that has multiple terms in the numerator, you can actually split them. Or if it was a subtraction problem, you can actually split them. Or vice versa, combine expressions. Meaning if you started with this, you could work your way backward to condense it into one. And then sometimes you have to multiply the numerator and the denominator by a binomial factor that appears on the other side of the identity. So if both of your equations on either side were divided by cosine, you can multiply by cosine and get rid of it. Stuff like that. That's when you would work both sides. The biggest thing is don't be afraid to stop and start over again. If you hit a dead end, don't get frustrated. Go back to the beginning and try it a different way. Sometimes what looks like it might be the easiest is not. So you just got to make sure you try again. All right, so let's start. It says verify the identity cotangent squared plus cosine squared plus sine squared equals cosecant squared. So which one is more complex, left or right? Left. What do you see on the left that you can replace? Cosine plus sine squared is what? 1. So right off the bat, I can say that cotangent squared x plus 1 equals cosecant squared x. And then go back to your trig identities. What is cotangent squared x plus 1? Cosecant squared x. Super easy. We're going to baby step our way in. Probably not on the same level as a test question. Okay? But you never know. Maybe you get lucky. Example 2. Tangent squared x minus sine squared x equals tangent squared x times sine squared x. Is there a Pythagorean identity with tangent and sine? Is there? Oh, yeah, but not a Pythagorean identity, right? Pythagorean identity either has tangent with secant or sine with cosine. So I can't use a Pythagorean identity, but I can use my inverse, right? Or my reciprocals. So what is tangent squared? What can I rewrite that as? Sine squared over cosine. Minus sine squared. Now, if this is over 1 and I want to combine that into 1 because there's no addition or subtraction on the right-hand side, I have to change them both to have what as their denominator? Cosine. So I'm going to multiply both the top and the bottom by cosine x here. Cosine squared x. I get sine squared x over cosine squared x minus sine squared x cosine squared x over cosine squared x. So I multiplied both the top and the bottom. Now my denominator is the same, so I get sine squared x minus sine squared x cosine squared x all over cosine squared x. Now what? What can I do with my numerator? Factor out the sine squared x. So sine squared x comes out. 1 minus cosine squared x. What's 1 minus cosine squared x? Sine squared x. So I have sine squared x times sine squared x all over cosine squared x. I haven't hit this yet, but I'm close, right? What can I do to get sine squared x times sine squared x over cosine squared x to become tangent x? Split them up. So I can take the sine squared x over the cosine squared x. Because it's multiplication, this is the same as what was written before. So when it's multiplication, obviously you can split them up. If that was addition, I couldn't do the same thing. And then sine squared x over cosine squared x becomes tangent squared x times sine squared x, which equals the initial right side. You've got to give me that last statement. So your left side has to equal the right side. You can't leave it as the one before it, assuming that I would know the next step. Hopefully I would know the next step. But you need to show that the left side equals the right side. So the very last thing that you should write is your equality statement.
Would you be able to leave your final statement as an identity?
You mean if it said sine squared plus cosine squared equals sine squared plus cosine squared? Like something like that?
If your final equation was...
Oh, if it said sine squared plus cosine squared equals 1, go the next step. 1 equals 1. So your last statement should always be identical on both sides of the equal sign. Because again, like I know you know that, but you can't assume. You've got to make sure you go to that last step. Okay, so when you move the cosecant, it becomes what? Sine. And when you move the secant, you do the same thing? It becomes cosine. So I end up with sine squared x plus cosine squared x. Then what? That's 1. And you can't go any further. Like there's nothing you can do with 1, right? So this is when you'd have to look at the right-hand side and say, okay, what can I do with that side? What is cosecant x? 1 over sine x. And then they cancel, and 1 equals 1. Anybody do the least common denominator on the left-hand side? Like cosecant x times sine secant x? That's obviously another way to do it, but that's a lot more complicated. All right, example 4, cotangent times 1 plus tangent squared over tangent equals cosecant x, cosecant squared x. Obviously, I'm going left side because it's a lot more complicated. So what do you see on the left-hand side that you could do? Is 1 plus tangent squared x something I can replace? Yeah, that's one of your Pythagorean identities, right? What is 1 plus tangent squared x? Secant squared. So I get cotangent x times secant squared x over tangent x. Now what? What happens if I bring tangent to the top? Becomes cotangent. So I have cotangent squared x times secant squared x. What is cotangent? Good. Cosine squared x over sine squared x times secant 1 over cosine squared x. Cosines cancel. I get 1 over sine squared x, which is cosecant squared x. When you're working, like I don't mind if you lose the variables while you're working. Just make sure you bring them back at the end. And don't lose your squareds. Be really careful with stuff like that. Good on that one? Yeah? Okay. Last one. So sine of x over sine of x plus cosine of x equals tangent of x over 1 plus tangent of x. So what side do you think you need to start working with? The left. So what can you do with sine and cosine? Can you replace sine with anything? No, right? Unless you're going to do the reciprocal functions, which is possible. You can work with it. Okay? But the bottom is not sine squared x plus cosine squared x. That's not your Pythagorean theorem. That tells me I got to work the right. So I'm going to look at tangent x. Okay? Tangent x would be sine of x over cosine of x over 1 plus sine of x over cosine of x. So now I've got everything in terms of my sine and cosine, but it didn't really make it any simpler. So I can't keep flip it until it's one term on the bottom, which means I'm going to change that.
From the first step, you just split it up.
Split it up in what way?
Tangent over 1 plus...
That's the other way around. So if your numerator is the plus or minus statement, then you can split it. But if it's the denominator, you can't. Does that make sense? If it was 1 plus tangent of x over tangent of x, then I can make it 1 over tangent and tangent over tangent. But when the bottom is the statement that has the addition or subtraction, you can't split it. If it was multiplication, you could split it, but not addition. And if it was in the numerator, you could split it, but not the denominator. All right, so then from here, I got to make 1 cosine x over cosine x so that I can combine those two. And I end up with sine of x over cosine of x all over cosine of x plus sine of x over cosine of x. Now I've got a fraction in the top and a fraction in the bottom. So I can change, flip this. Cosine of x over cosine of x plus sine of x. My cosines cancel, this is gone. And I end up with sine of x over cosine of x plus sine of x. Left side almost equals the right side. The only difference is the order. But addition doesn't matter. So it's sine of x plus sine of x. Over sine of x plus cosine of x. Questions on these? So your homework is a PDF because you're not going to get multiple choice on these kinds of questions. You got to show the work. And I know that you know what the answer is. The answer is on the other side of the equal sign. So you're going to just make sure that you work out all those steps. And again, don't freak out if yours isn't exactly the same as somebody else's if you're working with them, because you can get different methods but the same answer.
Why did you turn the 1 to cosine x over cosine x?
Here, you mean?
Yeah, why did you have
So before you can do that keep, change, flip to get rid of the denominator, it has to be a single fraction down there. So I have to combine the 1 plus sine over cosine into one fraction. So the 1 becomes cosine over cosine, and then you can combine them.